Hello again! Thank you for tuning in to the episode 3.4 of our video course Parallel Programming and Optimization with Intel Xeon Phi coprocessors. In this video, we will cover the fundamentals of explicit offload programming model through several basic code examples.
First, a quick review. Explicit offload is a pragma-based programming model for coprocessors. In the explicit offload model, the main body of the application is executed on the host, and some portions of the code which are marked by those pragmas are transferred onto the coprocessor and executed there. The offload model allows heterogeneous usage of Xeon Phi coprocessors, because you can offload only those portions of the application that benefit the most from the MIC architecture. In this video, we will use code examples to show you the basics of explicit offload. In the next video, we will cover more advanced offload topics like memory retention and asynchronous offload. Let's start by studying our code example. We'll be using a simple matrix vector multiplication code. The application first multiplies matrix A by vector B, which has different values in different iterations, and then stores the aggregated result into array C. Finally, it checks the result of the multiplication with the analytically computed result of this operation. First, let's compile it and run it on the host to confirm that we can get the correct result. Now let's try to offload the matrix multiplication to the Xeon Phi coprocessor. To offload portions of the code, we use pragma offload target mic. With this pragma, all lines of code within the scope of this pragma will be offloaded to the coprocessor and executed there. If we compile this code, we get an error. This is because with offload, by default, only local variables and arrays on the stack are transferred to the coprocessor, and dynamically allocated memory is not automatically offloaded. This is because at compile time, compiler doesn't know if malloc function call is succeeded and what memory block size we want to pass to the coprocessor. In our example code, we have dynamically allocated matrix A, which is used inside the offload region. Therefore, we need to explicitly take care of it. To offload dynamically allocated arrays, we must use one of the four clauses in, out, and no copy. In means the data is copied into the coprocessor at the start of the offload region, but is not copied out of the coprocessor at the end of the offload. Out is the opposite. Data is copied out at the end, but is not copied in at the beginning. In-out means that the data is copied both in and out at the start and at the end of the offload respectively. And finally, no copy means there is no data transfer. Here, we want to use matrix A inside the coprocessor, but we don't need to send it back to the host at the end of the offload. So, we will use the in clause to copy A over to the coprocessor, but not back. To use the in clause, you must not only specify the pointer, but also specify the length of the array you're trying to offload. Length should specify the amount of elements you want to pass and not size of the block in bytes. Note also that stack allocated variables such as vectors B and C and the matrix size n will automatically be copied into and out of the coprocessor at each offload unless otherwise specified. So we do not need to put them into an in or out clause. With this, we can now compile the code and run the application. And we can see that we got the correct result. Unfortunately, it is difficult to see whether the matrix multiplication was in fact carried out on the coprocessor. So let's use micsmc to check the status of the coprocessor as we run this application. We will also increase the problem size so that it is easier to see the load. When we run the application, we see the core usage bar for core 0 go up, which tells us that work was in fact offloaded to the coprocessor. Now let's imagine that we have taken this offloading code and copied it to a different system that does not have Xeon Phi coprocessors. We can simulate this by setting the environment variable offload devices to none. When we run the application, we get an error. Just to confirm, we can set offload devices to 0, which enables mic0 for offloading, and then run the application. We see here that the application executes normally when there is a coprocessor. This is problematic because this code is now system dependent. To resolve this problem, we can set the optional clause in our offload pragma. This makes the offload optional. If there is no coprocessor in the system, the code inside of the offload region will simply be executed on the host. We'll first try to run the code with a coprocessor enabled, just to confirm. And we see that the application still works. Now, we'll disable coprocessors and run the application. We see that the application does not return an error this time because the offload region was executed on the host. To verify that there was no offload, we can use the offload report. To enable offload report, set the environment variable offload report to 1, 2, or 3, where the number specifies the verbosity level. With verbosity level equals 1, the application prints which lines of the code performed offload and how long it took. With verbosity level 2, you will also be able to see the amount of data transferred. For instance, we can use this to verify that because we use the in clause for matrix A, the amount of data transferred from host to mic is greater than the data transferred from mic to host. With verbosity level 3, you will see more in-depth details about the offload like device initialization and individual variable transfers. Returning to the optional clause, let's run the code with offload devices set to none and the offload report enabled. Here, we see that there is no offload report, signifying that there is no offload. To confirm, if we set the offload devices back to 0, we now get an offload report. Now, we know how to make the offload optional. With the optional clause, if there is no coprocessor to offload to, the code that was designed for mic architecture will now be run on the host. To mark a portion of the code specifically for the mic architecture, or vice versa, we can use the preprocessor macro ifdef mic. At the compile time, the compiler makes two versions of the optional offloaded code, one for the mic architecture and one for the host. Macro mic is defined when the code is being compiled for the mic architecture and undefined when the code is being compiled for the host system. Note that this macro can be used for native execution as well. This is useful when, for example, you want to fine-tune an MPI code that has the same source code for coprocessors and CPUs in the cluster. In our example, we will use the preprocessor macro to add a task that prints which system the program is running on. If we run the application with offload enabled, we see that the code for the coprocessor was used. On the other hand, if we run this application with the offload disabled, we can see that the code for the host was used. One interesting thing to note here, unrelated to the preprocessor macro, is that the order of the print statements issued on the host and offloaded codes is not always respected. Console output on the coprocessor is buffered and then mirrored by proxy I/O in the host console, which may cause delayed output.
Thank you for tuning in. In the next episode, we'll talk about more details of explicit offload programming models, such as declaring functions you want to offload to the coprocessor, data retention and memory reusage, as well as asynchronous offload in the later episode.